It's okay. Yeah, I guess this is our cue. Hi everyone, and welcome to the second lecture in Giulio Tiozzo's mini course on Poisson-Furstenberg boundaries.
Thank you. Can I start? Okay, so welcome everybody. So this will be the second lecture, as Sami mentioned. I don't know what his face is here. Okay, so we'll talk about Poisson boundary for random walks and groups, and somehow I wonder whether I could. Okay. Well, anyways, so I will talk about Poisson boundaries for random walks and groups, and so today's lecture is a bit somehow is the core of the theory when we will actually see what is behind this definition and how do we actually prove things about the Poisson boundary. So the main tool would be entropy theory. So an entropy theory has been established mostly. So the Poisson boundary, of course, comes from Furstenberg, and the entropy theory comes from Kajmanovic mostly, and in particular, there's a famous paper of 83 or so, where it's Kajmanovic and Vershik. And then there's also other approach, which is similar, complementary by Derenic. So this would be the two main sources. So again, the idea is we defined yesterday at least some property, some universal property of the Poisson boundary, some definition of the Poisson boundary if you want, but somehow it's a very abstract definition. But the goal, of course, will be to, whenever you have a boundary in a geometric sense, to prove that this boundary indeed satisfies this nice property of the Poisson boundary. So for instance, you have representation for this harmonic functions. So remember, so what is the setting? So we have a measure group, so group, which is countable for us, and a measure on it. And this group acts by isometries on some metric space. And then, as we discussed yesterday, you pick group elements, a sequence G1, G2, and so forth, Gn, IAD, and then Wn would be the product. So this is our notation. And then you pick a point in your space, and you just do this walk by acting with this sequence, and in good situations, almost every simple path will converge to the boundary X. When I say good situations, I mean situations where you have certain hyperbolics, for instance, in a hyperbolic metric space, or even in other spaces like hyper space, where it's still not hyperbolic, but you have lots of hyperbolic directions. So then you define this hidden measure for the walk. So the hidden measure of the walk is just a probability, given a subset that the walk will hit that subset. And yesterday we introduced this notion of mu boundary. So notion of mu boundary means that you have your measure space which has a G action, and mu is a stationary measure, as we define it. And you also have a map from the space of paths to this space, which for us is just the map that associates to each path the boundary point. So this is the setting, and now the question is whether is this space that so far we defined using this limiting process, does it satisfy the property of the Poisson boundary? So which is, do you have a Poisson representation? So remember yesterday, we discussed the two spaces. So on the left, you have bounded harmonic functions. And on the right, you have measurable functions. But these measurable functions are on the boundary of X. So remember that in the Poisson representation formula, there's this duality. So you can go from a function which is harmonic on the inside to some measurable functions on the boundary. And vice versa, if you have a measurable function on the boundary, you can sort of do a convolution process, and you go to a function inside, which is harmonic. So let's recall what are these two maps. So in fact, in this abstract group theoretic setting, we have that one map is the Poisson transform that we already defined yesterday. So the Poisson transform goes from right to left. So the Poisson transform goes like this. So you start with a function in L infinity of the boundary. And then you define a harmonic function. How do you define it? Well, you have Pf. If you want to compute it on some group element G, well, what you do is pretty simple, in fact. You just take F, you take your boundary measure nu, we call it nu or nu mu, depending on the, but let's just call it nu, and you push it forward by this element G, so you have G just a nu, so you just push forward the measure and you integrate. So again, this is a very simple formula, but we said yesterday, we saw that it encapsulates all this theory of the Poisson kernel, because if we apply this to the group SL2R, and we work out this derivative, this Radon-Nikodym derivative that appears in this definition of this push forward, this is precisely this Poisson kernel that we have. So this is the equivalent of the convolution with Poisson kernel. Now, we haven't defined the other map. So the other map, as you said, it goes from, you see, from inside to the boundary. So you have a function defined inside. So you have a function, let's call it H, is a harmonic function on the inside. And we have to assign to it a boundary element. And so how do you do it? Well, in classical complex analysis, you just take the radial limit. But here we have no radial limit. We have no structure like that. But so that's where the probability comes to rescue, because the idea is you take this random walk and you look at the value of this function as you do the walk, and as the walk converges to psi, you assign to psi this limit. So how do we do it precisely? Well, the way to do it precisely is the following observation: is that if you consider H, so you consider Xn as H computed on this walk. So this process, so H is bounded and harmonic. So this process is a martingale. So maybe you have taken probability course a long time ago, maybe you never did. So let's recall what a martingale is. So martingale just means that the expectation of the martingale tomorrow, if you know what happened today, so condition to basically Xn, well, the expectation is the value of today. So on average, you're not gonna lose and you're not gonna win. If you know the value of the stock market today, on average, you're not gonna become richer or poorer tomorrow. I'm not saying this is true for the stock market. I'm just making an example, but somehow this is the idea. So, and in fact, it's kind of nice to write down this, for this particular function, we can easily write down why this is a martingale. So let me put the definition of martingale up here. I have still a little more space. So it's really easy to compute this expectation. So what are you doing? So you're trying to compute the expectation of this function h tomorrow. So at wn plus 1, given the state today, and basically it means that you know that wn today equals some element g. And what does it mean? Well, it's pretty clear. So maybe if you do like this, you will see better. So let's compute it. So, well, what do you need to do? Well, the value of, so wn plus 1 is wn times the next step. So this is h of wn times g n plus 1, because this is wn plus 1. And so what you need to do, well, you need to average over all possible futures. So you're taking the average of this over all possible futures, so mu of gn plus 1. So we're keeping, while keeping wn constant. So if you keep wn constant, you're just averaging, and then this is indeed just the definition of harmonic function, that this is equal to h of wn. So you see, everything sort of falls into piece. This definition of harmonic function and harmonic measures are given precisely so that you can do this martingale process. And of course, the martingale convergence theorem tells you, indeed, that there is a limit. So almost surely there is a limit. And so in the end, you define this inverse Poisson transform. In the end, you define this inverse Poisson transform by taking this limit. So you define lambda of this function h as the limit, as n goes to infinity, of the value of the harmonic function at along the path wn. And so this is basically you define this is a function on the boundary. So you want to say basically that this function at this function at a boundary point psi. So if you want to boundary point psi, it's the limit of this when you're conditioning. Yeah, when you're conditioning on hitting this psi point at infinity. If, let's say, if wn. So this is the notion of inverse Poisson transform, and it turns out that these two maps are inverse to each other. Well, not for all spaces, but precisely whenever we set this boundary to be the Poisson. So somehow that's an equivalent characterization. We want to choose some boundary so that these two maps are inverses to each other. And so then, of course, each of them is a bijection. Any questions so far?
I was curious. So in the case that this correspondence exists, if nu is actually G invariant, is that saying that the boundary is trivial?
Correct. That's exactly right. So you're anticipating some of what comes later, but it's precisely right. So in fact, right. So if there are, if the measure is indeed invariant, basically right. So you would think about this expression here. It means that you can remove the G. So it means that the only thing that you can produce with the Poisson through the Poisson transform is a constant function. And so that would precisely be equivalent to saying that the Poisson boundary is true. Precise. Other questions? Okay, good. So now I want to go in. So why does this space even exist? So, well, eventually we will have a geometric space, and we will have to prove that this geometric space does the job. But a priori, maybe we are concerned that this space doesn't even exist. And that would be a very valid concern, because in fact, the way you could define this object in the abstract measure theoretic sense is a little bit subtle. So now I want to delve a little bit into some abstract measure theory, which you might or might not like. I personally like it a lot, so you have to stick with it. So in fact, even without having any geometry, you could abstractly define such a space, except as you will see, the space will be defined in a pretty roundabout way. And so somehow it's way more satisfactory to have a concrete object to deal with, of course. Because the problem is this boundary is only defined, at least this Poisson boundary is only defined in the measure theoretic object. So you have a measure space, you have a group action, and you have a measure on it. But if you have an isomorphism of measure spaces which possess the G action, well, and the measure, well, then you cannot distinguish between these two. However, as Giulio pointed out, there are a lot of hidden measures for random walks. So even if I fix the space, indeed, there are a lot of measures. And it's kind of remarkable that in most usual situations, you would have a topological boundary that carries all the measures for a very large class of walks. So distinguish between them, it's a much harder task. Yeah. Okay, so what is this abstract definition? So we define. So remember this T. So this is a good exercise to test the audience. What is this T map? Yeah, yesterday we defined this T map. Do you remember what this T map is? So we said that there's two shift maps, right? So T is the shift. So remember that T is the shift in the space of increments. So T of Wn is Wn plus 1. Sorry, the shift in the space of paths. So the location of the walk doesn't change, but the time along the path. So what is the idea? So how do we naively construct a boundary? Well, what is the property that for sure we want of a boundary? Well, it has to be somehow, invariant by some asymptotic equivalence. So suppose you have two paths, right? So you suppose you have two paths. So two walks. So one is this walk, and then you have some other walk that, okay, maybe starts in the same, doesn't matter, goes somewhere. But then it goes exactly in the same location as the pink one. So you have a walk like that, and you have this other walk here. Well, whatever boundary notion you have, it better be that if two paths are the same after some time, they would be the same, they characterize the same boundary point. So that's the minimum requirement. And in some sense, it's the only requirement, except this in some sense is non-trivial. So we define the Poisson equivalence class by saying that two paths are the same if they're after some number of steps of one and some number of steps of the other, they are indeed the same. So in fact, yeah, so this means basically that you have two paths, right? So you have if you write Wn here, you have to say the Wn plus m on the one side, and Wn plus k on the one side, and W prime n plus k are the same for every k. By the way, there are two different equivalence relations that one can put on the space. So this would be an asynchronous one in the sense that m and n could be different. You could also put an equivalence relation which is synchronous, meaning that you just want the Wn plus k equals Wn prime plus k. So this one, these two are a priori different equivalence relations. So usually this is called the tail equivalence relation. And this is the other one is the Poisson equivalence. So, however, for groups, it turns out eventually that the two boundaries that you get putting either of them is the same. However, this is not true if you don't have a group. Like if you have an abstract Markov chain, it's more complex. Anyways, so this is the minimum thing we want to do. So now what is the natural idea? Well, the natural idea would be to quotient. You have an equivalence relation, you have all space of paths, and you quotient by this equivalence relation. And that you would have, in some sense, your boundary. However, here there are some problems. So what are the problems? The problems are that we want to work with this measure theory and this sigma algebras and things like this. And if you take the quotient just in this naive way, the quotient is not nice enough that you could actually do the measure theory. So I will say precisely what is the problem, maybe sort of briefly, because it gets pretty technical, but so sometimes taking quotients is really bad. So an example that in fact also works as a counterexample here is whenever you have a torus and you have an irrational foliation on the torus, right? So you pick an irrational foliation. So if your dynamics is somehow flow along this irrational foliation, the space of orbits of this turns out to be pretty bad. For instance, it's not Hausdorff, but even from a measure theoretic sense, is pretty bad. And I will tell you exactly what's going on. In particular, right, the flow would be ergodic, meaning that every subset, so every set which is a union of orbits, and it's measurable, it's either measure 0 or measure 1. So from a measure theoretic point of view, you can't really tell apart these different leaves. And so that's the heart of this problem. And so it happens in other areas of dynamics, but in this area, our map is just the shift map, but still you still have the same problem. Okay, so what happens here? So, okay, so what are the definitions? So, okay, so this is some abstract theoretic, abstract measure theory. So a Borel space is a space with a sigma algebra is standard if it's isomorphic to a compact metric space with the Borel sigma algebra. So these are the nice things, and usually we only work with these things. We really don't like to go beyond this category. And somehow it turns out, this is a deep theorem, that there's only almost one example, because all these spaces are basically, they are just the interval with the Borel sigma algebra. Plus, they could have some atomic part. So they could have some countable set of points. So these are so all the spaces that you think about, R, N, you know, the hyperspace, manifold, and orbifold, whatever, all the spaces that you do in geometry, they're basically all the same, except that they could have some isolated points that create that add some more structure, but you can have only find countably many. And so what is the property that characterizes the spaces? Well, a way to say it is to say that these spaces are countably separated. So what does it mean to be countably separated? It means that there's a countable collection of subsets that separates the points. So if I have any 2 points, there is one set that contains one unknown. And so this is basically the characterization. And so as we said before, so if you do the non-example would be if you take the circle and you do an irrational translation, or equivalently, if you go on the torus, you get an irrational foliation. So, and then you take the quotient by the orbits. So it turns out that such a quotient is not countably separate. And this is actually a pretty cool fact, which I might, yeah, we could even prove that. So basically, yeah, think about something like this irrational foliation. So yeah, you suppose that there is the separating collection. Then you can, for each n, you can find a finite partition. So what is the partition? Well, the partition would be you take the join of the partition given by Bn and Bk and Bk complement. So you can decide each point whether it's in Bk or in Bk complement. And so this is a finite partition of your space if you do it for the first n elements. And these elements are disjoint. But this map is ergodic, so there's exactly one such orbit that has one such element of the partition that has full measure. Just one. So for every n, there exists one element of this partition. Yeah, there exists some element, I don't know, Cn in Pn that has full measure. And these elements have to be nested if you do the n and the n plus one, because these partitions are nested. Right? So you know that Cn plus 1 is to be contained into Cn, but they all have full measure. So if you take the intersection of all these things, it also has full measure. So C, right? So if you take the intersection of all these guys, so this guy has full measure. But this guy is not one orbit. So since the space, the thing was separated, right? So being in C means that you know for each element of Bn whether you are in it or not. But this must be only one orbit, because this is separated. So Bn separating implies that C is just one orbit. But clearly, these two things are in contradiction. So this means it has full measure. This means it has one orbit. So it can't have. So this is contradiction. So the idea here is that this system is ergodic. On the other hand, yeah, it has too many orbits. So from a point of view of measure theory, you would only see one piece, but this one piece is not one orbit, because no orbit has full measure. So this is a very nice example that tells you that the situation when you take these questions is really complicated in a measure theoretic sense. And in fact, but the good thing is there is a way out by changing your. So the corresponding space, when you have a standard measure space, standard Borel space, and you also endow it with a measure, you call it a Lebesgue space, basically. And you call a partition. So this partition is a partition where each set is measurable. But this is not necessarily a measurable partition. What the measurable partition means that indeed, when you do the quotient, this quotient is counted. So in the previous example, you started with this foliation. This foliation is too fine, this partition. So you have to make it into much coarser partition, which in that sense is just empty set and everything. So this is the coarsest partition, such that you can, when you do the quotient is countable up to measure 0. So there is some morphology. But so this is the concept of measurable envelope, and this is a very famous theory of Rochlin and measurable partition. So in the end, the good news is there is some way out, and the way out is you start with any partition, but this partition maybe is too fine. So if you take the quotient, it's going to be too bad, but then you can take some coarser partition of that, so that it has a measurable partition. And so that we call this coarser partition the measurable envelope. You might have seen this term somewhere, and it means that you can take the quotient safely. And once you take the quotient safely, the Rochlin also tells you that the quotient also is nice. It's again standard, it's a Lebesgue. Any questions? So this is pretty technical, but I do want to point this out because it's kind of the core of this Poisson boundary theory. Why is it hard to characterize the Poisson boundary? Because the points of the Poisson boundary are defined in a somewhat roundabout way. It's like if you just take the set theoretic definition, the set theoretic definition has terrible properties from the point of view of the sigma algebra and the measure. So in general, you talk about the space of a ergodic component, which is precisely this. So you could say for any map, so any measure preserving map T on a space X, you can quotient by this equivalence relation that we discussed before, right? That two orbits are the same, 2 points are the same if eventually they coincide. And you take the quotient, but you take the quotient in this measurable sense. So you take this envelope, so this coarser partition, and then you quotient, and this is called the space.
So just the statement you made is that if the partition is ergodic, then the measurable envelope is trivial?
Yeah, that's right.
Okay.
So if the partition is ergodic, you only have either everything or empty, and that would just give you a point. And in fact, this is exactly once again one condition that is equivalent to triviality of the possible.
Thanks.
Okay, so in fact, now you probably guessed what is the construction of the Poisson boundary in the very abstract sense. So you can see that maybe you're disappointed, but that's all. That's life. Somehow you start with your space of paths, and you quotient in this funny way. So you do identify two paths if they eventually coincide. That's true. However, in the same class, because of this measurable distance, the class could be larger. So for instance, the idea is that there is no nice way to separate these points. So this walk converges maybe to different boundary points, but there is no natural way from in this measurable category to separate these points at infinity. Okay, and somehow what comes nicely, however, after this definition is a universal property, which is related to the following fact that by construction, so you have a boundary map, which is the quotient map. So from now on, I will call it BPF, the Poisson first order boundary. And of course, this comes with a measure, which is just the quotient measure, basically. And you push forward to by this quotient map. And interestingly, by this construction, you see that, in fact, in terms of the spaces of measurable functions, it's much more natural. What you see that the space of measurable functions on the boundary are the same as the space of T invariant functions on the path, on the space of paths. So in fact, you can think of this also in terms of algebras, like you can think of L infinity as a von Neumann algebra, and then you could say there is a spectrum of this algebra, which is somehow, again, the space of points. And again, it's kind of complicated to define what the space of points is. This is always okay. So that's some of the sort of scary part. So we're over it. So what we reap off of this is the universal property. So the universal property tells you that you can always produce maps out of the Poisson boundary. So in fact, you have your path space, and you have some other new boundaries, some other space with the G action and the stationary measure. So if you have one equivariant map one way, and you know that it's invariant by the shift, because somehow it's some asymptotic, depends only on some asymptotic property of the walk, then this map will factor through the boundary. So there is this boundary map. So there will be this G. And so this, in fact, is from the point of view of rigidity theory, this was the nice thing, because you can somehow automatically produce maps out of the Poisson boundary. And that's, in fact, what people like Furstenberg and Margulis used to start the superrigidity. But we're not so interested in that today. But the universal property is also another. And you see again from this universal property what is the uniqueness, right? The uniqueness is again up to this G equivariant measurable maps, because you can think of this as some initial object in some categories.
So this could be taken as a definition of the.
Yeah. This also could be taken as a definition. So basically, all these definitions are somewhat abstract. That's part of the problem. Okay, more questions? Okay, so now let's go to more concrete. So how do we actually have a handle on it? And that's why the theory of Kaymanovich and Vershik is very appealing, because it is indeed much more concrete. You can compute things. And so this is the entropy here. So let's start with just entropy of a measure. So you might probably have seen before definition of entropy, which is okay, you start with a measure, and you can define the entropy of a measure just by doing the sum of mu g log mu g. So the idea, of course, is that whenever you have a partition, the information, right? So it's like you have partition of your set. In this case, is given by the first step of your run and walk, and depending on the, if you do an experiment and you end up in some part of the partition, well, the amount of information that you gain by doing this experiment depends on how likely is your outcome. So here, what it makes sense to say that the information of this point X is log of 1 over the measure of the partition element that contains X, because if you're very lucky and you end up in a event which has very small probability, well, this gives you a lot of information. And also the log is here because you want some sort of additivity property. You want that two independent events, two independent sets of dependent partitions, so like independent experiments, so to speak, are such that the sum, when you take the entropy of the intersection, this will be the sum of the entropy. So it's like if you do two experiments and the information you gain from the first one plus the information that you gain from the second one give you the information of doing both. However, if they're not independent, then you need a concept of relative entropy, which we will see in a second, because sometimes the second experiment is somehow dependent on the previous. And so that's the idea, in fact, of the Poisson boundary from the point of view of entropy theory. Yeah. Basically, yeah. So basically, the idea of entropy of a random walk is the amount of information that you gain from one step to the next. So if I already done the walk up to step n and I do it up to do the next step, can I gain more information if I do one more step? So that's the definition basically. So the idea is this. So we take mu and we took the convolution of mu with itself n times, meaning the distribution of the n step of the walk. So you do n steps of the walk, and you took the entropy of the n step random walk. So clearly, if you do more steps of the walk, you gain more information. So the entropy is going up, but also you expect it to grow up roughly linearly. So every day you gain a little bit more of information. So this sequence is subadditive. That's somewhat pretty easy to note, that the entropy of mu n plus m, so you can work out this exercise, is at most the entropy of n step plus the entropy of the m step. And so then you can apply Feketa's lemma, and you see that this limit exists, like 1 over n, the entropy of the n step exists. And so this we call the asymptotic entropy of opposite. So as I said, you can be interpreted as the amount of information gained from one step to the next. So now the entropy criterion is the sort of the cornerstone of this theory. So very importantly, this theory only applies if the entropy in the first step is finite. And however, you do have measures that have very spread out and such that I have infinite entropy. And that's a big problem. And there's some small progress has been made, but basically all this theory really works only when the entropy is fine. Okay, so but the cornerstone says the triviality criterion. So if you want to say whether the Poisson boundary is trivial, this is equivalent to the asymptotic entropy being 0. Very nice criterion, and there's three groups of people that proved it roughly at the same time. And so in particular, well, this has immediate consequences that for group theory. So if you have a group with sub-exponential growth, so the number of elements in a ball of radius n is sub-exponential, right? Then the Poisson boundary is always trivial, at least let's say for finally supported measures, right? So the thing is what that you want to say that sub-exponential growth means that 1 over n log of the number of elements g such that the word metric is less than n And if this is going to 0, well, the thing is the entropy, 1 over n, the entropy of the n step of the walk. Well, we know that the entropy is always bigger than the cardinality of the support. Right? That is a fundamental property of the entropy that we didn't write, but it's a. So whenever you have that you walk, so okay, so if the boundary, so if the walk has finite support instead of like, so well, you maybe need to add some constant here, depending, because your walk will be supported on a set which has diameter growing linearly with n. But if the number of elements grows sub-exponentially, well, the entropy can only be 0. So in some sense, these groups with sub-exponential growth are somewhat not so interesting. However, yeah, there's more tricky things because, in fact, for non-amenable groups, we know that the boundary is non-trivial. But then there are still some very interesting category of groups, which is groups where they have exponential growth, but they're still amenable. And then there, the theory is really subtle, and there are like even very recent advances in it. Okay, maybe any questions so far on this basic definitions of entropy and entropy criterion? Okay, so I want to give you proof of the entropy criterion actually. So so to do that, we need to look at the notion of relative entropy. So, and we have to look at this various partition. So so this proof is the proof of Kaymanovich inversion. So if I have two partitions, so I can think about the relative entropy of one partition with respect to it. So what does it mean? It means I have a space and I do one partition. So this is maybe the psi partition. And then I have another partition that I don't know how it is. So this is the eta partition. So of course, so if these two partitions were independent, well, the probability of the intersection of one element in the common refinement of the intersection will be just the product of a probability of the piece of the partition in one partition times the probability of the element of the partition in the other. Of course, if these two partitions were the same, then the entropy, relative entropy, should be 0 because you don't gain new information. And so here's the definition of relative entropy. So this notion psi of x and eta of x means what is the measure of the element of the partition that contains x. So what's the idea here? The idea here is that I fix the outcome of eta. So suppose I don't know, I fix the outcome of eta. This means I fix some class with respect to eta. And now I look at the entropy for the conditional measure on this subclass. So I want to look at, for each element of psi, what is the probability that I choose this particular element of psi, given that I've chosen this particular element of eta. So this is the formula, right? So this is like the probability of choosing both at the same time, and this is the probability of choosing the element of eta So, and then you integrate that, that's the relative. Okay, so yeah, the figure, I guess we already drawn. So what is the idea here? What do we want to do? So we want to consider the relative entropy of different partitions. So we have a whole set of partitions here. So in particular, two types of partitions. So you have your walk. So you have a sequence of head partitions and sequence of tail partitions. So head partitions means that you just identify elements that have the same starting pattern. So let's say that this is WK. So the head partition of level K means that two parts that are in the same element of the partition, they start to the same. Then they can do different things later on, but they start the same. So this is the alpha K head partition. And then there's a tail partition, which is the one I was discussing before, which is we can do whatever we want at the beginning, but eventually your trajectory is prescribed. So after step K, your trajectory is prescribed. So you start to whatever you do, eventually you're gonna. So this is WK, and this is the tail partition. And so you see that, so this is kind of interesting because, so the head partitions, as you increase K, the partition becomes finer and finer because you're remembering more and more at the beginning. The tail partition is the opposite. You're forgetting the beginning, but you're keeping the end fixed. So the tail partitions become coarser and coarser as n grows. And so in the end, for the Poisson boundary, we care about this elusive Poisson partition, which is the coarsest. Yeah. So this partition is coarser than eta n for every n. So this partition is somehow, is by definition the coarsest partition. No, it's it's coarser than, it's the finest partition that is coarser than every eta. And again, it's kind of tricky to define it. You need to go through this measurable partition business because it's not just a set theoretic. But in any case, that's the idea. So what is the idea of Kaymanovich and Vershik is you look at the relative entropy between these two types of partitions. So you're fixing, so you have some n. So, okay, so let me draw the picture. Let's keep the definitions here. So what happens here? So now there's a calculation, which is a bit tricky, but so what do you want to say? I mean, not so tricky. So you fix the end step of the walk. Suppose you know the end step of the walk. So you're fixing the tail of this walk. So this walk is predetermined after. And then you look at some stage before. So you look at WK. So if I know that I'm going to end up here, let's call it G, this point, at step n, and I also know in the first K steps. Yeah. So we know G1, and this is G1, G2, and so forth. And so this is, we know all this, yeah, basically we know all the increments. So let's say that. So this, of course, is W1, W2, W3, and so forth. But you don't know just that. You also even know precisely the path, not just the endpoint. So you know G1, you know G2, G3, G2. And you know this G here. Now in the middle of the walk, you could do a lot of stuff. What is the probability it happens? Well, you can compute it because this is, after all, a run walk. So you see, you have to fix what's the probability that all this happens, of the intersection of these events, the fact that you're here at the beginning and you're here at the end. Well, you see that you have to choose these things at the beginning. So you have mu of G1, mu of G2, mu of GK. And then you have to jump from this one all the way to here. You have to jump in n minus k steps. And the increment, well, you have to end up in G, and you already know G1, GK. So the increment, the last increment is this one, GK minus 1, blah, 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 G1 minus 1 to G. And the denominator is just the probability of yeah, so sorry, say here. So here, the probability is, in the denominator, is just the probability of hitting G at time. So it might take a little bit, but this is the most important one. So once you do this, you can compute. You could compute precisely this entropy because, well, the relative entropy is just you take the log of this guy and you integrate. And so you get this formula up here. So what is H? Yeah, recall that Hn is, maybe I didn't define it, is the entropy of the nth step of the walk. So what it turns out is that you have the following thing. So you have the starting part takes into account. So the starting elements are independent of each other. So the total entropy is the sum of k times the first step entropy. Because you remember all the paths, not just the endpoint of the path, but every single step. And now this part tells you, gives you the entropy of the n minus k step. And this part in the end gives you the entropy of the n step. So, okay, maybe you want to do the computation again by yourself, because I realize it is slightly, slightly tricky, but this is the idea. Are there any questions? This is a very, very important. And now from here you can take the limit as n goes to infinity, because this partition that you have in the back, the tail partition, when you take the limit, it will converge to this Poisson partition. And so this will converge to the relative entropy between the kth partition, the kth tail partition, and the kth add partition and the tail partition. Okay, so what is the consequence of this, as I said? So basically, you start with the nth step. So you look at the limit as your n goes to infinity. You're forgetting more and more things at the tail. Eventually, if you can forget all the things, you get the boundary partition. Please ask some question, because this is non-trivial. So it would be helpful if someone asks some question. So you see what's happening here. So So what we want to quantify is the difference in entropy here. So H infinity, area infinity is the tail partition, is what happens, as I like to say, at the end of history. So if you know what happens at the end of history, what choice do you have today? This is alpha 1. So how much information, if you already know your destiny, how much information can you gain by knowing this choice? And that is the key point to estimating whether the boundary is trivial or not. And so you apply this formula here. You take n to infinity. Let's say if k equals 1, well, what do you get here? Well, you get, so this is the entropy of the first step. And this is the difference between the entropy of the n-1 step and the n step. And this one is, by definition, the asymptotic entropy. The asymptotic entropy was the average, but it's also the same as saying the limit of consecutive difference is the same as the limit of the average. Right. So this is the asymptotic term. And so see that happens whether if the entropy is 0, the asymptotic term is 0. So if the asymptotic entropy is 0, means that this term is 0, means that the relative entropy between today and the end of history is just h of mu. It's just the entropy of today. For every, and you can repeat the same for every k. You have the same formula for every k. So if h infinity is 0, means that the entropy of knowing the first k steps, given the last step, so to speak, at infinity, is the same as knowing the first k of the first k steps. And then this is the, so you see that the relative entropy, yeah, so if the relative entropy equals the entropy in the first k steps, means that the first k steps and the last step are independent. And so if this infinity partition is independent of all the finite partitions for every k, well, all these finite partitions generate the whole sigma algebra. So it means that this finite partition has to be trivial. Again, trivial modulo null sets. So this is a beautiful proof of Kaimanovich and Vershik. I understand that it takes some time to grasp it, but it's a very interesting idea that you can quantify, because this idea appears in other areas. You can quantify whether two events are independent by taking the mutual entropy. And so if the mutual entropy of two events is the same as the entropy of the first event, it means that these two events are independent. And you can quantify it by because this is a random walk. So somehow, once you know how to condition the random walk on the first k steps and the last step, somehow you can still compute things because the steps themselves are independent. So you can come. Okay, so this is the core proof. Now, so this is good for triviality of the boundary. So we call the entropy. So triviality of the boundary is good, but it only addresses some class of groups, but maybe not the groups we are really interested in. Especially the groups Khazar is interested in, like the mapping class group or relatively hyperpolling groups, because the boundary there is non-trivial. So what do we need to actually make this workable in that situation? Well, you need a relative notion of this entropy criterion. So this will be the last, and this will lead us to the sublinear tracking property. So we will start seeing the geometry, how. Okay, so let me tell you. So what is the relative entropy? Well, the relative entropy for a random walk or conditional entropy is the following. So you have your walk, and your walk, you already know it converges on a boundary. So, and you want to say whether the idea, of course, is the following: whether you look at all the paths that converge to this boundary point, and the question is, how many are there in some sense? And the way to quantify it is, can we further split the boundary in some even smaller, partition, so that the relative entropy goes even further down? I mean, the idea is like, if I know that this walk converges here, I can associate the notion of relative entropy. I can take all the paths that converge to that point and measure the entropy of that set of paths. And the idea is that if that relative entropy is zero, you're taking the right boundary. So think about it. If you could say, okay, suppose you can always take the trivial boundary. You can say, okay, you compactify everything to one point. Then you have all the possible paths. But all these possible paths converge to the same point. But now, if there is positive entropy, means that you're not taking the correct boundary. You could further split this boundary apart and lower the relative. So the idea of relative entropy is that you have a notion, I guess I wrote it here. So you have a notion of measure of a conditional random walk. So you fix your point psi, and this is the distribution of a random walk condition to hitting psi at infinity. So you don't consider all the paths, but only the ones that hit psi at infinity. But this is still some process. However, it's no longer a random walk, because it's a random walk that you already know it converges to psi. So it's called conditional random walk. And you can do a computation, and maybe I will skip to, in the interest of mentioning the final theorem. So it's some other process on the group. And what enters in this formula is the Rodin-Nikodym derivative. So nu is the hidden measure for the starting random walk. And so, okay, so this is the distribution of the original random walk. So if you want to go from the origin to G in n steps, mu and G would be the original distribution. And this is the Rodin-Nikodym derivative of hidden measure. Why do you do that? Well, the reason why you do that is because you want to somehow push this walk to converge. You want to push this walk to converge towards psi. And so the Rodin-Nikodym derivative does exactly that. You can write some formula to convince yourself of that. But so in any case, this is not quite a random walk, but it's still a Markov process. And then you can have a relative entropy criterion. So relative entropy criterion is the same thing, except it's relative. So you conditioned to hit one point at the bound. So yeah, well, the picture is the same as before. I can do the picture. I mean, the picture is the same as before. So you have your xi here, and you have, and you look at all the paths that hit psi at infinity, and you associate some entropy number to that. And the criterion is precisely that this boundary that you've chosen from geometry is the correct boundary if and only if for every boundary point, this conditional or relative entropy is 0. So the idea, it means that since the relative entropy is 0, means that the boundary cannot be further split apart. You see that on the one hand, I mean, it's much nicer to rephrase it in terms of entropy, because we saw that to define it set theoretically is a mess. You take apart this point in the set theoretic way, and then take a sigma algebra. But the entropy theory just does it, because it's precisely characterizes at the level of sigma algebra. So if the relative entropy is 0, it means that your boundary is large enough, so you have enough points so that you can reach this representation. And so this brings us to the final thing I want to talk about, which is the sublinear tracking property, or the ray approximation criterion. And tomorrow we will discuss more about it, and then we will actually apply it to some situations. Okay, so this is a much more concrete and geometric criterion, but it comes from this entropy criterion. So, okay, so we start as a measure, we say it has finite first moment if the average step of this measure, average distance traveled by the random walk in one step is finite. And then if you have a group action, you want to say that the action is not too bad, in the sense that in a ball of radius r, there are at most some exponential number of group elements. So these are reasonable assumptions. For instance, if you have a finally generated group acting on itself, but also in most other cases. So the ray approximation criterion tells you the following, and it's related to this sublinear tracking property. So it says the following. So basically, you have your group action, and you have some boundaries, some geometric boundaries, some bordification of X, meaning some space in which X is dense. Well, it need not be compact, in fact, because this is a measurable theory. So the compactness usually helps in the first part to prove that the random walk converges, except I already proved several times that this is not needed in general cases, and in this paper with Pascal Gillen also. But somehow, in general, that's where the compactness helps. But if you know that the walk converges, the other thing you want to know is that for every boundary point, you can consider, for instance, a geodesic, or maybe in the spirit of this mini course could be even quasi-geodesic ray, that, for every boundary point, I construct a quasi-geodesic ray from the origin to that point. And then I consider the location of the random walk at step n. So if the location of the walk is close to the geodesic, and L is the drift, so just to rescale the geodesic on the right. So if you know that the distance between the walk and the geodesic is sublinear in n, I'll show you, then this boundary is the right one. And here we don't need to prescribe gauge, like following up on yesterday's question. So as long as it's sublinear is enough. And I will tell you more tomorrow why this is indeed the right condition. But the basic idea to connect with what I was talking about is that if you have a sublinear tracking, means that once you fix a boundary point, you measure the relative entropy. So the relative entropy means of this set of paths that converge to excite. But you know that these paths are pretty constrained because they have to lie in this ball. They have to lie in a ball around gamma of Ln. The entropy of this set is sub-exponential because the ball has a radius that grows sublinear. So this idea I will go back tomorrow, but the idea is indeed that if you have the sublinear tracking, we get as a byproduct, we get that the relative entropy is zero, almost sure. Because you have a control on your walk, because it has to lie in this ball. And so then you can measure its entropy. That's okay. So I think I'm